Okay, I think I'll begin. So when I was putting this lecture together, I was sort of reflecting on this material that I've been putting together and my own grappling with understanding it over the last decade or so. And so I think this is a brilliant photograph of satellite imagery of sort of the way we've transformed the world, at least in terms of light at night. And I think before this it would just be pitch black. And so it's really, really staggering. And so I think one of the things that I think is really bizarre about our existence is we get born into the world and we have stable institutions, schools, high schools, parents. The buildings don't change very much. The roads are there. There are laws and rules and regulations. And your parents talk about it and your grandparents talk about it. And so we come into a world of sort of relative stability. There's sunrise, sunset, summer, winter, Halloween, Christmas, Hanukkah, whatever it is. But as you look on a deeper time scale, which is what this lecture is about and what the last few lectures have been about, it looks like we're actually on a roller coaster that's getting faster and faster, beginning to get out of control. And we don't have that sort of visceral experience of our own place in the world. But as we start to look at the historical records, we can see that things have been dramatically and radically changing over the last few thousand years and the last 100 years or so. So the world that we live in now is utterly different from what it was, say, 200 years ago, which is utterly different from 5,000 years ago, which is utterly different from 10,000 years ago, which is utterly different from 100,000 years ago, which is not so different from 200,000 or 400,000 or a million years ago. So we're actually kind of on a roller coaster, and it's hard to sort of mentally get up to speed with that, given our sort of day-to-day experience of life from sort of our first memories to now. And so what I want to talk about then is, this is where we are, sort of four things. The first is sort of climate change over the last million years or so, and then extinctions as we colonize the globe. Was it us? Was it climate change? Was it both? Then extinction in modern times, ask the question, are we in a sixth mass extinction or not? And then finally, what our role is in modern climate change. And we're talking about the short-circuiting of the long-term carbon cycle. So starting off with climate change over the last million years, and in terms of this is sort of a review of some of the material that we've looked at, both in my lectures and also Elliot's. And so I just remind you, I've shown you this a couple of times. So this is the end of the Cretaceous when the dinosaurs disappear and the ammonites running up to the recent. And this is the average global ocean temperature as measured by carbon isotopes, oxygen isotopes in fossils. And here we can see we have this steady decline in temperature over the last 15, 20 million years or so, and dipping ever increasingly so to the recent, with these major oscillations being the major ice ages, for example. And so we've lived in this world of general global cooling on that geologic time scale. And so if we zoom in and look at the last 5 million years average temperature, so here's the 5 million years of temperature change from sediment cores. And so there's lots of short-term oscillations. And then starting at about 2.6, 2.7 million years ago, the temperature then starts to dip. And the oscillations get larger in magnitude. And so early on, these oscillations are controlled by the 41,000-year Milankovitch cycle. And then in the last million years or so, it's been the 100,000-year, roughly, Milankovitch cycle that's been dominating the periodicity of warm, cold, warm, cold. And when it starts to get cold enough, the cold can start to produce major ice ages. And there have been about 10 of them in the last million years or so. And so I think that's what I was going to say. Yes, that's right, yes. And so what do we think was happening about 2.5, 2.6, 2.7 million years ago? What happened? That's the emergence of the genus Homo, not Homo erectus, but the first Homo. This is where we first getting the first stone tools, those simple ones that last for about 1 million years. So in this period here, and then Homo erectus is originating here somewhere. So as the globe starts to cool and as the seasonality starts to increase, I think it puts pressure on food availability in Africa and East Africa, and we have the emergence of Homo at this point. course, Australopithecus is further back in this stage here. So just to remind you, the 41,000-year cycle is related to this wobbling of the tilt, which controls the degree of seasonality. The higher the tilt, the more intense the seasons. And so this has about a period of about 41,000 years. And then the roughly 100,000-year cycle, there are other resonances, is got to do with the degree to which the orbit is more or less elliptical. And so when it's more elliptical, the Earth finishes up further away from the Sun at one point and a little bit closer at the other. So you get increased seasonality at that time scale. And Elliot provided you with these numbers of a variation in the order of 25%, depending on where you are in that cycle or not. And so these orbital, these astronomical features are the features that sort of dominate these temperature variations on shorter timescales. So geologic processes are probably responsible for the general decrease. There's less CO2 production coming out of volcanoes on the seafloor. And then the shorter oscillations have to do with these orbital variations. And so just a reminder then that as we came out of the last ice age now about 20,000 years ago, so this is 500,000 years, so 20,000 years ago is just in here. Elliot showed this diagram here of sort of the extent of the ice sheets, which are extensive but not vast, but particularly in the northern hemisphere. And also note the drop in sea level. So during the ice age, you could walk from Papua New Guinea to Australia, or you could walk from France into England, etc. So one thing the literature discusses a lot is the forcing of the climate system, the Earth's orbit, CO2 on life. But what isn't as appreciated is the fact that life can feed back onto climate change. And I'm going to give you two examples of that. So the first one here is there are some researchers here at Berkeley who have, for about a decade, I think, put heaters up in the field in Colorado. And so they've been simulating climate change by having an increased temperature, and you can see that it basically melts off the snow where the heaters are. So that's equivalent to a couple of degrees Celsius higher each year. And so that's nice, but what they found interesting is that because of the higher temperature, there's been a replacement of one type of plant with another type of plant, and the new plants are darker, so they absorb more sunlight, so it's warmer. And so it turns out that a 20% change in regional plant cover in this part of Colorado will have an effect on local summertime climate equivalent to doubling CO2. So if you replaced all the white footpaths in a city with black footpaths that absorb more sunlight, it would be warmer. And so the vegetation itself affects the local climate. We call this albedo, the degree of reflectance. So there's less albedo, more absorption. So one thing that climate models don't do yet is take into account the fact that as vegetation responds to climate change, then the amount of sunlight that gets absorbed or reflected changes. And I'll give you one more example where this seems to have made a rather spectacular difference. So if we look at the rate of retreat of the North American ice sheet at the end of the last glacial maximum, about 21,000 years ago, this is the rate of retreat of the ice in kilometers per year. I don't know what the numbers are. There's the value there. And the climate models basically assume that as the ice retreats, it exposes bare rock. And bare rock tends to be very bright colored, so it reflects light well. But it turns out that, and I'll show you in a moment, that as the ice sheet was retreating, there was spruce forest growing up against the ice sheet as it moved north. And spruce is dark color. And so models with trees growing at the ice sheet edge predicts a faster retreat rate because the trees are absorbing heat, which is melting the ice off faster. And so it turns out that the empirical measured rate of ice retreat you can only get right when you put the vegetation in, and the fact that the vegetation is changing, growing up against the ice sheet. And so again, this is the sunlight absorbed. So this has got high albedo and this has got lower albedo. And so here's just a diagram illustrating the effect. So this is a place called Yosemite, or as my daughter says, it's not Yosemite, it's my-semity. So it's become my-semity now in the household. The rock is really bright. And so it was filled with ice, which has carved out the valley. As the ice retreated, if it just remained bare rock, a lot of light would be reflected back again. But it's been filled in with this dark forest, which absorbs the sunlight, heating the ground, causing the ice to retreat faster. So very, very important to take into account the feedback between forest, in particular, vegetation, and the climate itself. And so here's a spruce. And so this is 25,000 years ago, about the time that the ice sheet was at maximum, 14,010, 7.5, and now. So here's the ice sheet melting, and here are sort of where there are pollen data from cores, and this is the guesstimate as to where the spruce forest was. And so as the ice sheet retreats, the spruce grows right up against the edge of the ice. So rather than exposing bare rock, there's always this forest growing up against it, which accelerated the rate at which the ice retreated. Okay, so that's that principle. So back to the climate change. So here is the average global temperature over the last 400,000 years. This is based on Antarctic ice cores. And so what I'd like you to note is that this is an ice age. Sorry, this is warm. And we go slowly into an ice age, and then abruptly out, and then slowly into an ice age, and then abruptly out, and then it gets a little bit erratic, but slowly colder on average, abruptly out, fairly abruptly in again, and then slowly colder and colder, and then abruptly out again, and here we are here in the last 10,000 years or so. So the ice time is longer than the non-ice time. The interglacials are short, the glacials are long. So most of our evolution, and most of the plants and animals in the last 500,000 years, in fact, 1,000,000 years, have been largely at cold times, not at warm times. So we are in a strange climatic time where it's unusually warm over the last 1,000,000 years, even though it's been repeatedly fairly warm as we come out of the glacials rapidly. So that gives you a sense of the backdrop of where we are. Now, it turns out that the amount of ice frozen at the poles is large enough to have a fairly serious effect on sea level. It draws down sea level by about 100 meters or 120 meters, 350 feet. And so Elliot showed you this slide here. So for most of the last 1,000,000 years, you could easily walk from the continent to England. It was not an island. There is no English Channel. And so that would have been the extent of the land at the last glacial maximum, with some ice sheets sitting in the highlands of Scotland. So that's the norm over the last 1,000,000 years or so. And here's another spectacular example. This is one of the famous examples of island biogeography, biodiversity hotspots. So this is Borneo sitting in here. Here is Java. Flores of Flores Mans just out here. Bali, I think, is this one. Komodo Island, where the Komodo dragon lives, is in there. This is Sumatra, Malaysia, Thailand, and they're running up into mainland Southeast Asia. So this simulation here shows you what happens to the sea level over the last 1,000,000 years. And I put 1.069 because here it is, 1,000 and 69,000 years intervals. And so this shows you again, asking the question, is Borneo a good place to do island biogeography? Let's try again. Fat fingers. So the ice time is when the sea level is low, the green is high, and you can see that all of these places, Vietnam, Cambodia, Laos, is attached to the peninsula of Malaysia and Thailand, connected to Sumatra, to Java, to Borneo. Wallace's line sits in here, which is the water's deep enough that you couldn't get across to further east. So you can see most of the time it's actually connected, not disconnected. And then we're running to the present now here. Boom. So again, the flooding is fairly recent, right? Really spectacular. So we live in this strange world. And for big trees, this is only about 100 generations for a big tree, which is not that much in terms of evolutionary time. Okay. So what I want to do now is look at extinction as we colonize the globe. Was it us? Was it climate change? Was it both? And so, again, I remind you from a previous slide, Homo sapiens first appears in the fossil record 160,000 years ago. It was probably earlier than that. We just don't have the fossils. And then by the order of 100,000 years ago, we get out of Africa, 40,000 years in Europe, 70,000 years in South Asia, 50,000 years in Australia, 15,000 years in Alaska, about 12,000 in the lower 48, 14,000 in South America, presumably a separate route boating down the coast rather than going by land. Don't know the details there. So what's interesting, so this then is the oldest Homo sapiens there, and again in a time of Ice Age. It's in Africa, so it's not particularly cold there, but in the time of Ice Age. And so one of the questions is, how does Homo sapiens affect the world? And there are different ways. Our impacts, other than hunting, we can alter the habitat by simply fragmenting the habitat, putting cities in, knocking down forest. We also bring with us dogs, rats, cats, pigs, camels, and they cause huge devastation. Left out goats in local areas. Hyperdisease, we introduce diseases. And then we also sometimes just kill things directly by overhunting. But we can also have slow overkill. And so it turns out that we've had enormously huge impacts wherever we go. And so islands are one of the best examples, and human impact is depressingly clear. In the Pacific Islands, estimated there are 8,000 species of birds or populations that have gone extinct. Roughly 20% of the bird diversity in the last 10,000 years. Lots of flightless birds that have been wiped out. In New Zealand, 60% loss of bird species, including nearly all the flightless birds. The kiwi and one flightless parrot being the only two that have survived. Madagascar, 50% of its lemurs, small, cute primates, all greater than 10 kilograms, are extinct. 2 hippo species, 2 giant flightless birds, the elephant bird and the tortoise. So we get on islands and we just seem to kill things. And we do it really effectively and quickly. And that's just the way it is. So these next slides are based on a compilation by Tony Barnowski. Tony's a faculty member at Berkeley here. And this is him with Governor Brown. And so a bunch of us organized a meeting and published a paper in Nature recently talking about sort of our impact on the planet. And it caught the attention of Governor Brown, which is really spectacular. And so a lot of what's been happening in Sacramento has been initiated by Tony and his colleagues, including myself and others. So I want to now look at large mammal extinction dropping back in time. So there are these extinctions that occur around the time of the last ice age. This is split up by North America, Australia, Africa, and South America. Globally, there are about 97 genera that went extinct. Giant ground sloths, short-faced bears, saber-toothed cats, giant vulture type things. There's also a lot of genera that disappeared from at least one continent. So in North America, 50,000 years ago, there were horses, camels, a lion, 50% more massive than the African lion, which are now gone. The horse is back, having been introduced from Europe, but it's a different, obviously, horse population.
Do we know that the American lion looked like?
Did it have a mane?
Yeah, as opposed to a mountain lion.
Yes, I don't know. There's no way of knowing whether it had a mane or not. So we don't know how sexually dimorphic males and females are as a function of size. Male and female tigers, which are larger than lions, don't have any pronounced dimorphism. Male differences from female differences, so good question. And so here is the number of species that exist in each of these continents that survive the end ice age mass extinctions. And here are the ones that go extinct. And what's interesting is that almost everything that's extinct is big. So there's been preferential extinction of large body sizes, which is interesting. So now what I'm going to do is just go quickly continent by continent and see if I can answer the question, was it us, was it not us, was it climate, was it the two of them acting synchronously? So this is called the megafaunal extinctions, mega as in just big animals, and the body size is greater than 44 kilograms. Why pick 44 kilograms? This is a pseudo-metric number, not a metric number. How many pounds is 44 kilograms? Anybody know? 100. So this is basically extinctions of things more than 100 pounds. And then they've converted it into metric, so it's got this silly-looking number 44, which looks strange. So this is 100-pound animals. And so these are the extinctions, globally extinct, things that survive elsewhere, and this is the number of survivors. And so Australia has the highest extinction rate. 88% of them have gone. There are only 2 mammals now greater than 100 pounds. 2 kangaroo species. There are about 30 kangaroo species, lots of little ones. And so when did this happen? So here's the origin of Homo sapiens. Here's roughly Homo sapiens arriving in Australia. So again, during glacial times when it's cold, about 50,000 years ago. And so this is, for example, one of the victims in Australia. There are wombats. I should have put a wombat picture in, sorry. Did anybody know koala bears? So the nearest living relative is the wombat, which is basically like a terrestrial version. And this is a giant wombat, about the size of a small cow. So it's a pretty big wombat. So these diagrams are a little bit complicated. So this shows you the number of genera that were driven to extinction, about 21. These boxes are sort of in different time chunks. Once carbon dating stopped, it's really hard to tell time. So they've been chunked into 40,000 to 28,000 years ago, 51 to 40,000 years ago. Carbon dating kind of dies. Sometimes less than 80,000 years ago, but more than 51. And the numbers here are the number of genera where we know when they became extinct. So 6 and 6 and maybe 1 a little bit younger. And this is human arrival. It's fairly uncertain. But they're fairly synchronous. It's difficult to measure in the fossil record because it's very bad in Australia. But it looks like most of these extinctions coincide with human arrival in the order 50,000 years ago. Where in North America, the extinctions are much later, about 10 or 12,000 years ago. Now, what's interesting, so then lesson from Australia, humans alone can cause extinctions. There's no change in the climate during this time interval, but it may take a while. It looks like it may have taken in the order of 5,000 years to wipe it out. And if you think of an overkill type hypothesis, if losing every member of a species over 5,000 years just translates to just a few % per generation, which means that if I'm a kid and I see the giant wombats wandering around the place, and now I'm an elder of the tribe bringing up my grandkids, the number of giant wombats on the landscape look pretty much the same. I can't tell the difference between 99% of the original number when I grew up and 100%. So here's a case where I think the Australian Aborigines probably had no idea that they were driving them to extinction. Because for every couple of generations, there didn't really appear to be any change in the numbers. This slow incremental disappearance. So that's really, really important. And it happened so slowly that population declines would not have been noticed, particularly in the absence of any written records, which was true there. So what happens when ecosystems, when you put humans and global warming together? So let's go to North America. Pretty severe extinction rate, still 72%. And so there's Homo sapiens in Africa, Australia. This is when Homo sapiens arrive in Western North America as we're coming out of the last glacial into the interglacial. And I want you to draw attention, this is going to be important later in the lecture, to this blip in the climate data. So the temperature goes up and then down again and then goes up again. So this is called the Younger Dryas. The Dryas is the name of a tundra wildflower. And so here's the data expressed differently. And so this is time going the other way, 40,000 years to the recent. This is the average temperature based on the ice core data that Elliot showed you. And what you'd like to notice that in Greenland, there's oscillating backwards and forwards, Milankovitch, and then we can't start to come out of the ice age and then fall back in again and then finally come out properly. So the Younger Dryas is this little return to almost ice age conditions. What is interesting is that you don't see it in the southern hemisphere. So it's only a northern hemisphere phenomenon. And it's taken a long time to convince people that this is true, because most of the science is done in the north. And so it's often talked about a global return. It's just in the north. Oh, yes, and there's the wildflower for which it is named. You get a return of this tundra wildflower in the fossil record of this interval, and then find it goes back way up into the north again. And it's Dryas octopetala. So how many petals does it have? Right. So occasionally scientific names make sense. Often they don't, but sometimes they do. So what caused it? Here's our best guess. So here's a map of mostly Canada and the northern Midwest. Here's Lake Superior, Lake Michigan, Lake Huron. So this is Wisconsin, Michigan, Minnesota. Looks like there was a giant lake that caused by the melting of the ice sheet as we came out of the last glacial. And it looks like there was an ice dam that melted. And this lake catastrophically drained into the Atlantic, coming through this way, through the St. Lawrence Seaway and into the Atlantic. And the hypothesis is that if you flush an enormous amount of cold, salt-free water into the North Atlantic, you change the transport of heat that the Gulf Stream brings to Europe and North America. So the Atlantic Ocean flows up past Massachusetts and then off to Europe. And so Ireland and England sit way north of Boston and New York, but are warmer. And the reason is you've got this hot, warm water coming up from the equator with all the fogs and everything else coming in it. If you flood that with a huge volume of cold, ice-free water, salt-free water, you basically shut down that transport of heat to Europe. And you go back into an ice age for a while. So that's the hypothesis, a catastrophic change, in this case breaking of this ice dam, releasing this fresh water. Not sure for sure, but I know when I was an undergraduate, the idea that anything catastrophic happened was basically off the table. And now we've seen catastrophic changes happen quite a lot. This is a small catastrophe. The formation of the moon was a rather large catastrophe. The death of the dinosaurs was a pretty decent-sized catastrophe. So the idea that things can be fine for a while and then change dramatically now has become part of the way we think scientifically. So here's a picture of Californian megafauna during the glacial interglacial cycles. And I remind you that they survived about 10 of these. But it's only in the last one that they disappeared about 10,000 years ago. And so we really do think that the difference between then and what happened 10,000 years ago is this. We have the arrival of these guys. And so the thought is very much that the human arrival in the Americas basically drove the megafauna to extinction. And the size selectivity has to do with the fact that big animals are easy to catch and their populations are smaller, so it's easier to wipe them all out. So in Alaska, the megafauna start to go extinct around 13,500 years ago, and it's a little bit earlier, later when most of them go extinct in the lower 48 states. So the extinction at the end of the Younger Dryas looks like it could have been in as little as 300 years. So you would notice that. Your grandfather would tell stories of how easy it was to find mammoth compared to now. So that's fast.
And this is across North America?
It's across North America. Most of our record is in the West and also some in the Midwest. So we don't really know what's happening in the East because we don't have a fossil record there. But these animals migrate big differences, so it's probably across the whole country. Good question. South America has a very intense extinction scenario. We have a current grant from the National Science Foundation to actually get the chronology right because we don't know what it is. Lots of radiocarbon dates. South American humans arrive earlier. Megafauna seem to go extinct So there seems to be a more extended time of co-occupation in South America than in North America, in the order of 3,000 or 4,000 or 5,000 years. Question.
Do we know
If South America had what?
Like a rainforest?
It looks like the rainforest during the Ice Age was less. It was drier. Most of these extinctions, actually, interestingly, are recorded in here. The fossil record on the Amazon is dreadful. It's flat. It's covered in trees. There's no way you can get buried easily. Things just rot. So we don't know much about what's happening in the Amazon basin at all. So most of it's centered around Patagonia, the Andes, Chile, Colombia. So anyway, so stay tuned on what's happening there. We're just writing some papers up now with about 30 South American colleagues who are vertebrate specialists. Question.
So humans arrived in South America earlier than
Yes.
North America?
Yeah. So it looks like there were two routes. It looks like what happened is that there were sort of fishing communities that came down, and they've left, and then they became farmers in here a little bit. They've left an archaeological record. Some claim they might have come directly across the Pacific, which is also possible. I don't think so. I think they probably just came down. And then in North America, it looks like they came across via the internal route that Leslie had talked about, and was sort of not fishing coastal people. It may also be that we will just find things that are older at some later point. So, for example, one thing which is a nuisance in the Bay Area here, Leslie talked, I think it was Leslie, it might have been Tim, the Emery Shell Mound on Emeryville, which has this sort of huge record of human occupation. It goes back about 3,500, 4,000 years. We have no archaeological evidence of Native American peoples going back to 10,000, 12,000 years ago in the Bay Area. And the answer is, why not? What was the sea level 10,000 years like? It's about 100 meters lower. So where was the coast? The bay was high and dry, completely empty. You know the Farallon Islands? You can see them out past the Golden Gate. That's where the coastline was. That's where everybody was living. So all the archaeological sites have been drowned by sea level rise since the melting of the Ice Age. So we don't have a record of that first 5,000 or 6,000 years of human occupation because it's sitting out there 20 or 30 miles under the ocean. So it's a real nuisance in terms of getting back to the earlier history there. Okay, so North America, lessons from the lower 48 states. Extinction and diversity loss is severe and fast when you combine humans with climate change. Europe and Africa. The megafaunal extinctions in Africa, it's hard to know, but look like they were much reduced. And maybe it's just because the animals grew up with us. They knew to keep away from us. Also, it's a really dangerous place. And so I just don't think humans ever gained the population numbers relative to the wildlife in Africa as they did when we invaded elsewhere, where animals had never seen humans before and had no idea how lethal we were. There's also plenty of nasty diseases in Africa that didn't exist, for example, in the Americas. And so I think there are lots of things keeping human population down. Europe, human arrival is in the order of 40,000 years ago. There's some extinction when we arrive, and then there's a scattering of extinctions for the next 10,000 years or so, ending at the last ice age. So our impact is much more diminished than the Americas or in Australia. And I think this is a good story of the sort of thing that happens. This is the mammoth story. So this sort of climate modeling, guessing where it's good to be a woolly mammoth. They like the cold. So this is the last interglacial 126,000 years ago. And they really only like it where it's really cold. So they're up on the northern edge here of sort of Siberia and northern Europe. And then when things get cold again, 42,000 years ago, 30,000 years ago, the woolly mammoth is in good shape. It likes the cold, it's thriving. And so the black dots are where we have sort of fossils. And then what we have 21,000 years ago, humans now, so here's humans. Humans don't like the cold. And so there's the human extent, there's the human extent. So it looks like basically the mammoths had the north and the humans had the south. And so there's the range there. And then what looks like happened about 6,000 years ago, it's fairly late, is finally humans just started, population numbers go up, we get better at living in cold places, wipe the woolly mammoths out as we finally properly colonize Europe and Asia. So coexistence while it's cold, and then when our numbers finally go up, we wipe it out. And there are a few populations that survived to about 4,000 or 2,000 years ago on some islands that miniaturized that we couldn't get to. So lessons from Eurasia. Extinction did not occur until human populations increased and climate change at the same time. So there are different patterns, but all the while it looks like humans are heavily implicated in the extinction of all these large mammals across the globe. The timing corresponds to our expansion, etc. So in some respects, we live in a strange world for the last 10,000 years, where the last 2 or 3 or 4 or 5 or 10 million years of history of large mammals has been wiped out. And we're in this strange world with no saber-tooths, no cats, no giant ground sloths, etc. Okay, so we've seen a huge loss of megafaunal taxa. So large mammals have a major impact on vegetation and produce greenhouse gases such as methane. So cow flatulence makes a difference to greenhouse gases, to global warming. But it turns out about 90% of the gas actually is burps. Cows burp a lot, and they produce a lot of methane. And methane's a much stronger greenhouse gas than CO2 is. And so farming both methane from rice paddies but also from agriculture actually has a measurable effect on the climate. And so a question for you guys, how does the megafaunal biomass today compared with the biomass prior to the megafaunal extinctions during the last ice age and at the end of the last ice age? So much less, a little more, much more. So what's the biomass today of megafauna compared to the biomass, say, 100,000 years ago? Okay, we've got some greens, a little more. Got some reds by the looks of things. What else we got? We got blue a little less. No whites, not much less. Okay. So the answer is much, much more. So where's it all coming from? Where's it all coming from? Us. Yeah. We tend to leave ourselves out of nature, but there's us. We're a megafaunal species. And so that's where our body mass is. So we're a small megafauna, but we're still there. We're well over 100 pounds on average. Well, some of us are. So how does it change if we add humans in? So we are a megafaunal species. So here's a diagram of human population growth. So really sort of not measurable on the billion-person timescale for a long period of time. So megafaunal extinction occurred when human numbers were low but growing. So in Australia, 50,000 years ago, this is a log scale, double log scale. And then this is 10,000 years ago in North America, 13,000 years ago. And so here now is population numbers and species. So this is the megafaunal extinction. This axis is the number of megafaunal species. Mammoth, mastodon, there are a couple of species of mammoth. And so here is the decline due to human extinction and then the big drop at the end of the last ice age. And this is human population growth as far as we can guess. And interestingly, this is when first agriculture kicks in, which I find kind of interesting, is our population numbers start going up as the megafauna goes extinct. And the megafauna are mostly gone at about the time that agriculture starts to kick in. So again, we switch from a hunter-gathering to an agricultural type way of living in this time frame. And I know it varies a lot by continent to continent. So it's a little bit hard to just generalize in this fairly simple way. And so here's the Australian megafaunal extinctions in the order of 50,000 years ago, and then sort of Eurasian, and then the Americas with the youngest ones about 11,500 years ago. So there's the loss and population numbers now beginning to increase. So as we hit critical global population size, we hit global population size at the same time that climate changed. And at that time, half of the world's megafaunal taxa went extinct. So dramatic change starting about 10,000 years ago. Now this now is a conversion of that graph into estimated body biomass. How many tons of humans are there versus elephants versus camels, etc. So this then is the loss in terms of biomass of megafauna, extant plus extinct. And this is the biomass of humans. So we cross over about, I don't know what that is, 5,000 or 6,000 years ago. Here's the same data adding in humans with the megafauna. So this is humans plus extinct plus extant megafauna. Here's the extinctions versus agriculture. And this increase here is entirely due to human increase. So it looks like it took about 10,000 years for human population numbers to increase enough to replace the megafauna. So that's really slow, and that there looks like in the order of about 100 to 200 years ago. So for most of that time, there was less megafaunal biomass than there had been before the extinctions. And so human biomass replaced extinct megafauna, surpassed biomass baseline, again, about 10,000, 9,900 years ago. But it turns out that the biomass is actually a lot greater than this. So what have we left out so far in terms of megafauna? There are other things that are pretty high body masses. There are lots of. Cows. And if you count pigs and sheep, our livestock. So you put our livestock in. That's the mass of the megafauna plus humans. There's the megafaunal extinction. There's human growth. And then with the Industrial Revolution and industrialized farming, we produce huge numbers of livestock. And so in terms of biomass of large-ish mammals, it now vastly exceeds what was there before the megafaunal extinctions. So it's not just human biomass, it's all the animals that we farm that have spectacular impacts on the planet. And of course, a lot of deforestation is for farmland, which includes both crops but also livestock. So once you put us in, the picture is radically different from the one you might have had in mind prior to that. We are part of nature, and it's important that we include ourselves in our description of it. Okay. So now I want to turn to this question of extinction in modern times. Are we in a sixth mass extinction? And what I mean by modern times is in the last 100 and 150 years. So our impact on the globe in the last 100 years or so has been rather spectacular. Here's a nice figure from Google, looking at forest change over 12 years since 2000. And so first, the green is basically where most of the tree cover is. So there's the tropical forests. And there's the boreal forests up in here, and then tundra up in the far north, so it's only forest. The red is loss, so that's where the primary loss is, the Amazon rainforest. This purple is a little bit misleading. This is where there's been both loss and gain. And this is a little bit misleading, because in Southeast Asia, in Sumatra, Malaysia, Thailand, and in Borneo, it's purple. And so what's that? It's the knocking down of the rainforest so we can grow oil palm plantation. So we're replacing thousands of species of plants with one. And so the insect loss and the mammal loss is vast. So it's a little bit misleading. It looks like we're doing fine, right? We're just changing the species of the plants. Well, not really. We go basically into the barren wilderness of the oil palm plantation. Papua New Guinea is one of the few places that just hasn't been touched yet. And there has been some regrowth in some areas, particularly in Europe and also in the Americas. So there's some forest coming back again. And I haven't got the pictures of it, but if you look at historical photographs of California compared to now, there are a lot more trees in California than there were 100 years ago, in the foothills of the Sierra, etc. So there's a lot of reforestation in the temperate developed nations. So here's another depressing figure, deforestation in Borneo, 1950 to estimated 2020. There's 2010. So this vast island has been almost, well, it's not almost deforested, but there's not much left. And a lot of that is actually non-Indonesian or Malaysian countries coming in and logging for their own domestic markets. One of the issues in ecology which we're dealing with theoretically is, do you hit catastrophic changes as you exploit the world? And so this is the famous story of the cod fisheries. So this is cod yield. Things look like they were fine. Boom. They hit some critical threshold where suddenly the cod basically disappeared. And the fishery just collapsed. Economic disaster for the New England fisheries. Now there's a few that weren't driven to extinction, but you can see this is the yield of fish taken out. And the way we fish the world is phenomenal. This is the global footprint of European fishing activity, so this does not include Japan, China, Korea. So in 1950, that was the extent of extensive fishing. With the huge ocean-going trawlers now, this is the extent of the this is at least 30% extraction of raw resources out of the ocean. So our impact on fisheries, if you love sushi, which I do, depends on where your sushi comes from. So myself, I don't eat tuna anymore. As much as I love it, I just go for the salmon. So absolute phenomenal impact in the oceans, which is invisible to us. We don't see the oceans very often. Lots of sharks being killed. This is what happens when you take out top predators to reefs. They don't knock back lower down in the food chain, so you get these cascades if you take out the top predators in ecosystems. So you get these cascading effects like we saw with the cod. And so we're trying to grapple with this at the moment, and a bunch of us from Davis, Berkeley, UCLA, Wisconsin, Cal Academy, NASA, Google, I've forgotten a few, are putting together a huge grant at present to try to set up a science technology center to try to actually forecast this properly in a way that we can actually responsibly act in the world. And so actually I had a meeting earlier this morning discussing that. So now let's go to extinction rates as opposed to just ecological degradation. So here's the extinction intensity over the last 540 million years. The increased volcanism of the Permian traps for the end Permian, the meteorite for the end Cretaceous. And so one of the questions is, are we in a sixth mass extinction? So the last 540 million years, the Earth has experienced 5 major mass extinctions. How do current caused extinctions compare? Now, I'm not talking about the ice ages. I'm talking about us now, industrialized Homo sapiens. So much worse, a little bit worse, not quite as bad, hardly comparable. Compared to the end Permian or the end Cretaceous, for example. So get your bits of paper out, discuss it. Where are we? Okay, so hold up your sheets of paper. So we've got some that are saying much worse. We have some a little bit worse. We have some not quite as bad. We've got some reds hardly comparable. Okay, so there's 2 components to this, so I'm going to answer each of them separately rather than put this up. So the first one is by magnitude. It's simply the number of species that are extinct. So these are the big 5 mass extinctions, and this is actually at the estimated at the species level. So there's the end Cretaceous with the dinosaurs. There's the end Permian with trilobites going extinct with about 96 or 98% extinction. So these are the big 5 mass extinctions in terms of species level extinction. And this is where we are today. I'd say much less. Now, this is the actual extinctions, so it's barely comparable. And the black ones are if everything that's currently put it on the endangered species list go extinct. So actually, at present, it's actually barely comparable. In the last 100 and 150 years, we've basically driven virtually nothing extinct in comparison to everything that's alive, which is actually good news in that sense. And this is what it will look like by magnitude if everything that's currently endangered goes extinct. So in some sense, we have time to act with these ones. So by magnitude, we are not in a mass extinction. Now, how many people think that 9/11 was a bad thing? Pretty catastrophic, right? How does it compare to the destruction of World War II? Doesn't even count, right? 2 buildings, good heavens, as opposed to 2 nuclear bombs in Japan, the sinking of huge ships, massacres of armies. It doesn't really count. So to my mind, in some respects, using the mass extinctions as a metric for what we're doing today is a little bit out of kilter. Just because it isn't a mass extinction doesn't mean that it's not serious. It doesn't have a major impact. So I just want to indicate that this is the highest possible high jump bar. And what about rate? So this diagram is complicated. The bottom one is the magnitude of extinction, which we've talked about. The y-axis here is the rate, which is extinctions per millions of species per year. We don't know in the fossil record how fast things happen, but here's the extinction rate estimated for the end Ordovician when the shallow seas drained off the continents with the Ice Age. Here's the estimate of the rate for the Devonian. There's the estimated rate for the end Permian. We don't know what it is. Here's the estimated rate for the end Cretaceous. It could have been really high if everything went extinct on a bad weekend. The meteorite strikes and everything is gone, right? That's a really high rate. But it might have been that not many things went extinct due to the impact, but due to climate change in the aftermath of the impact that might have taken 1,000 years, so the rate might have been much slower. If we assume that the big mass extinctions, everything went extinct in 500 years, and there's the rate. If everything went extinct in 500 years for each of those mass extinctions. Here's our current rates for things that we've already driven to extinction, and here's the rates if endangered species go extinct in the next couple of 100 years. So by rate, we are in a mass extinction. The loss of species is as fast or faster than the globe has ever experienced, except perhaps with the exception of the end Cretaceous. And so one of the questions is, does that increased rate, even though the magnitude is low, have unfortunate consequences for, say, food webs and further ecological collapse? And that's one of the burning questions which we're trying to answer. So by magnitude, we're not in a mass extinction. By rate, we are, but it's a little bit bogus because if still a lot of things don't go extinct, well, then it's over. So some of the hype with the 6th mass extinction is, in fact, hype. But it doesn't mean that we aren't changing the world radically, which we are. Okay, so I want to finish up with our role in modern climate change and the short-circuiting of the long-term carbon cycle. And so here is the inferred temperature from the ice cores, and here is the measured from the ice cores CO2 concentration, which you can see follows the temperature fairly closely. And so then as we come out of the last ice age, the CO2 is higher. I want to remind you that the cause is not the change in the CO2. The cause is the orbital wobbling, and the CO2 then follows. And we'll get to that a little bit later if you have questions. So here now is a 1,000-year time scale, and this is inferred departures from temperature. The average, the baseline here is the average temperature from 1961 to 1990, just arbitrarily picked. And so 1,000 years ago, it was a little bit cooler, and there were all these oscillations going backwards and forwards. And then starting in the 1900s, the temperature starts to rise, and then rise and rise. So that's the long-term climate. So we're definitely on the 1,000-year timescale. It's never been warmer. And then if we zoom in and look at CO2, here is CO2 measurements now starting, 500 million years ago again. So here's the into the ice age out, into the ice age out, into the ice age out, into the ice age out. And then this is the human contribution since industrialization. Question, sorry. Gone again. Okay, sorry. So the maximum was around 280 parts per million. So there isn't that much CO2 in the atmosphere. and then it dropped down to about 180, and it's been doing that. And now we're up to about 395. At the moment, it's going up at about 1 per year is the rate. And here's the projection, one of the projections for 2100. So how long ago? That's what, 90 years from now? So most of us are unlikely to be alive at that time, right? Unless you live to 110. But there's the projections of the rapid increase of CO2 vastly exceeding what the globe has seen over the last million years. So one of the questions is, this is an incredibly rapid change, and so it's led to predictions of both magnitude of change, number of degrees Celsius, and also the rapidity. Turns out that these changes are not exceptional in the last 100,000 years or so. So here's a diagram here. It's a little bit complicated. The y-axis is the magnitude of change in degrees Celsius, and the x-axis is the rate of change, the number of degrees Celsius per 1,000 years. And this red envelope here is the envelope if we double CO2. We get to about 560. So it's about there. So if we double CO2. And it depends on where you are going to be in the globe as to what that impact is going to be in terms of temperature. So the rate is high, and the magnitude can be lowish to highish depending on where you are in the globe. It turns out we went through a similar rate as we came out of the Younger Dryas that I talked about. So that brief return to Ice Age conditions, and then as we came out, the rate was similar. So one of the things that we're doing with the University of Wisconsin actually is looking at the fossil record of how the vegetation cover changed, because that's the same speed as is changing now, as is projected to change. And then by magnitude, the Earth was frozen pretty bad during the last glacial maximum, 21,000 years ago. So in terms of magnitude, we came out fairly slowly, but the magnitude is huge. Went from a world with big ice sheets. Now, it's going in the other direction. It's getting warmer, not colder. But we do have then historical records of similar magnitude and similar rate changes. But we haven't seen both combined. The magnitude and rate is unprecedented in the last million years or so, and perhaps ever. Okay. So then here then is the record since 1880. And again, I think the 0 point here is the temperature at 1980 and the CO2 value. So the CO2 value is the black line here. So it's just been steadily rising since industrialization with an acceleration after World War II. And then here's the temperature compared to 1980. So it goes up and down and wobbles, but it's on average much warmer in the 2010s than it was older. So there's the global temperature change. And one of the questions you get is this just due to CO2 concentration, due to human activity, or is it perhaps due to change in the solar radiation? And so here is a graph of the change of solar brightness, for the one of a non-technical term, since 1980 to 2005. And so the sun has this cyclicity and the rate at which it produces energy. I think that corresponds to the sunspot cycle, is that right? So the sunspot cycles, they're more and less, and it corresponds. The amount of change in radiation is tiny. This is 0.05%. And so if you look at these oscillations from 1980 to 2005, they're not really visible in here. I think some of these little kinks might be it. So the change in the sun's luminosity looks like it's been unimportant in this trend here. The CO2 dominates it. So in terms of measuring the CO2 increase, the best place to measure it has been on top of one of the big volcanoes in Hawaii. And so here's the classic diagram of the measured increase in CO2 on the top of Mauna Loa in Hawaii. And you see, again, this steady increase. And what's interesting is also notice that it wobbles on a yearly cycle. And so one of the questions is, why is it wobbling? So why does the atmospheric CO2 measured in Hawaii drop during the spring and summer and then rise again? So what's going on here? Why is it doing this? So increased sunshine due to summer holidays, so less pollution, less CO2 production, due to vegetation growth, due to decreased rates of plant decay. So what's the answer? Okay, what have we got? So we've got some greens and some blues. So it looks like the answer actually, and it's important, is actually most of you who've voted are half right. It's due to vegetation growth, but also due to decreased rates of plant decay. And I want to remind you of this aspect of the fact of cycles. Everything is cycling in the atmosphere, the ocean, and the vegetation. And, well, you could have said increased sunshine. Why is vegetation growing? Why does it grow in the spring and not in the winter? Because it's getting warmer. There's more sunlight, it's warmer. So in some respects, the actual driver is the increased sunshine in the northern hemisphere. So, in fact, that would have been a perfectly good answer. So I just want to remind you of the short-term carbon cycle, or part of it. So atmospheric CO2 is taken in by photosynthesis, which consumes CO2. So where's the CO2 going? Where's the CO2 going during photosynthesis? Sorry? It's going into sugars, which are a precursor of cellulose. It's going into wood, right? Wood, leaves, roots. So CO2 is being drawn out of the atmosphere and being converted literally into trees, into plants. And then what happens? Those plants get eaten or they decay, and so it's respiration, and that produces CO2. So what happens when you breathe out? You breathe out CO2. So you're returning back to the atmosphere the CO2 that you were taking in by eating your food. Right? So that's the pump question. I did. Okay, so that was a misstatement on my part. What I said is that plants are absorbing more heat, and that heat is equivalent to increasing CO2. It's not actually producing more CO2. It's saying if you take the temperature increase due to just absorbing more heat and say how much CO2 would I need to increase that, that's the equivalency I was making. So the absorption of heat is not producing more CO2. So that's a really good clarifying question. So what happens is when you get spring growth, there's lots of CO2 being pulled out of the atmosphere, converting into vegetation. And then what happens in the fall and winter? There's decreased rate of growth. You shed your leaves, and so things now decay or get eaten and produces CO2. So you can see then, each year, you can see the spring growth and through the summer, the spring growth through the summer, and then you can see the stop of growth and the decay. So you can actually see that transfer between forests and the digestion of forests and the annual cycle. So it's measurable on Hawaii, which is really spectacular. So you can actually see this functioning in Hawaii every year. Spring and summer growth followed by not. And then on top of that is the CO production. Now, one of the reservoirs in the long-term carbon cycle was the ocean. And if you remember, there was about 56 times more carbon in the ocean than in forests or the atmosphere. Probably don't remember the 56. So what happens to a lot of the CO2 in the atmosphere? It gets absorbed into the ocean. So here is the atmospheric CO2 with that yearly cycle in it. And the blue here is the concentration of CO2 dissolved in seawater. So a lot of that CO2 is actually getting in the seawater. So there's actually more CO2 production than you would think, because some of it stays in the atmosphere and some of it dissolves. And what happens when you dissolve CO2 into water? It becomes more acidic. And so there's the pH, the acidity. So there's ocean acidification measured directly in Hawaii again. The increased CO2 production, a lot of it actually dissolving in the ocean, and that dissolved CO2 in the ocean is producing an increased pH. So it's directly and easily measured, which is really kind of scary, actually, in terms of coral bleaching and things like that. So I was really annoyed when we had a job interview candidate from Stanford when I was at Harvard who said, atmospheric CO2 is not really a problem because it's, the ocean is a huge sink for CO2. What? It's not a problem because it's coming out of the ocean, atmosphere into the ocean? Yeah, right. So what happened about 1960 is for a long time the ocean had been a CO2 source, and now it's become a sink. So we've switched the way the biochemically coupling happens. So human perturbations to the carbon cycle. Over the past 100 years, human changes, deforestation and burning has increased CO2. So you burn a forest, it doesn't grow anymore, and all that carbon gets released, so that also releases CO2. But the biggest change is due to the burning of fossil fuels, an acceleration of the long-term carbon cycle at about 100 times the normal rate. So we've basically become a potent geologic force. And so I just want to remind you then, if we take the amount of terrestrial biosphere, basically trees, and call that amount of carbon 1, there's about the same amount in the atmosphere, 6 in the soil, there's the 56 dissolved in the ocean in terms of inorganic carbon. And then the amount of carbon that was in rocks is vast. And so the organic carbon in rocks is what? 2 names. What do we call it? The organic carbon in rocks. What's it called? Oil and coal. Right? That's what it's called. So this is oil and coal. And you can see the amount of carbon is vast compared to what's currently in the forests. And so what we're doing is we're mining that out, burning it, releasing the CO2 that's taken hundreds of millions of years to accumulate. So here's a graph of the coal deposition on geologic time. So the Cambrian explosion about 540 million years ago. Here's the recent. No coal deposition until about 360 million years ago. Why? Why is there no coal deposition in here? None. 0. There weren't any plants on land yet. Right? Cambrian explosion of animals, and then it takes a long time for the first forest to appear. So no forests, no coal deposits. And then big coal deposition in this time with these giant first forests after the invaded land with these giant insects that we looked at. And then sporadic coal deposition for the rest of the geologic history until the present. So basically we find these places and we do this to it. So this is a coal deposit that corresponds to those carboniferous coal deposits. So this is a huge thickness of ancient forests piled on top of each other that corresponds to these, accumulated over tens of millions of years. And we're burning it in tens of years or centuries, releasing all that CO2 in the atmosphere. So this is the acceleration of the normal return rate of carbon in the atmosphere. And then the oil is spectacular as well. So anybody know where this is? Some of you have seen this picture. This is essentially downtown LA. These are the oil fields in Southern California. How many have been to the Getty Institute? Where's its money come from? Anybody know? It's oil. The Keck Foundation, the Keck Telescope, it's oil. So a lot of the wealth in California, particularly Southern California, was oil. Black gold. In Northern California, it was gold, and earlier. Anybody know where this is? Yeah, someone recognized it. Yeah, it's Huntington Beach. About 60 years ago. Looks rather different, right? So that's where the wealth of Southern California comes from. The source is diatoms, microfossils that were deposited about 10 million years ago, so it's a very young oil. And this one is also one of my favorite pictures. Anybody know where this is? One of your professors grew up there. About there, I think, somewhere. This is West LA, 1920s. I forgot the name of it. What are these hills there? You go through on the way to LAX. LAX is sitting where this place is here. So there's sort of Santa Monica Beach, Venice Beach, running down into Redondo and Manhattan. Downtown is sort of behind me this way. La Brea tar pits are somewhere in here. So look at that, eh? Just spectacular. Suck the oil out and then change it. And so that's what it looked like in the 1920s. It's now got a city on it. So, 20,000 years ago it looked like this, where the La Brea tar pits are. And now it looks like this. So fantastic transformation of the countryside. So the bottom line is industrialization, our huge population numbers, and our capacity to mine oil and coal, and now with fracking, means that we're fundamentally changing the composition of the atmosphere. We become a potent geologic force, short-circuiting the geologic carbon cycle and turning into a short-term carbon cycle as we return back to the atmosphere carbon that took hundreds of millions of years to accumulate. And so we're going to shift gears now for the next lectures, which is to look now at the possibility of life elsewhere in the universe. This lecture has some bearing of that, and Elliot's going to go into that in some detail in future lectures, which is what's the probability of finding life as complex as us in the universe. And what we're going to look at is, starting with life in extreme environments on Earth, what is it that actually makes life go? And then we're going to start to look, or Elliot will, at other remarkable places in the solar system where life might or might not exist. So, until next time.